Okay, I just want to emphasize one thing before we get going, that these epsilon strips, so here I've drawn the epsilon strip, it needs to hold for all values within what you're claiming the delta strip is. Okay? So I'd like everyone to draw the delta strip for this function. All right, so this would be our delta strip here. There's our delta strip. And then what do we take delta to be? We take it to be the smaller of these two. So I think that the one on the left, again, ends up being the smaller of the two, but that's up to your ability to draw straight lines. Okay. Any questions on that? All right. So this is the take-home question from this section, and this is tough, folks. I often have people, they try to come at this their own way. And sometimes they're right, but it's pretty rare. Okay, so this is one of the few times where I just say, if you don't understand this, that's okay. I'm not concerned if you don't understand the epsilon delta proofs. It takes, like I said, I think it takes a couple of years to really master these. Okay. So what are you going to do then? Well, then you're just going to copy me. You're going to mimic me. So this is one of the first things, the few things I just say, just memorize this. Okay. But the problem is that people they don't believe me when I say memorize the word order. And so they kind of just give something that's like the word order. This word order is very precise. Okay? So we'll see that here in just a second. So this is my steps for going through this. The first thing I think you need to do is you need to come up with a guess. Okay? So in all of these problems where we've drawn our epsilon strips, we drew them about what we thought the limit should be, right? So we need to have our guess. So basically, in math, a lot of times by the time you get around to proving something, you already pretty certain it's true in your gut. And it's just you're dotting your I's and crossing your T's for your reader. Okay? So when I say we're going to take a guess at the limit, I don't mean like as a random guess. I mean basically you're going to have the answer before you get started. Which is why I've said these problems aren't very illuminating. You don't learn a lot about the function by doing the epsilon delta proof. It's how you just formally prove it. Okay? So we need a guess. What's our guess at what this limit should be? Well, we think
6.5 between 7.5.
I mean, how could we evaluate this limit? Let's use our tools from chapter 2. Yeah, we can use direct substitution on this, right? So Logan, we were close, but what do we get here? We get 7 as the limit. That is our guess. Now, by guess, I mean this is the right answer. I'm actually proving this. Okay, this is our maybe candidate is the better word. The candidate to be the limit. Okay? So we've got our guess. The next thing we do is the most important work for you guys as the students, as the writers of this proof, but it doesn't count for the proof. And that's often confusing. So I call this section the scratch work. And the goal of the scratch work is to find a formula for delta. Generally. So here we go. We're going to go ahead and assume that epsilon can be made to be greater than the absolute value of our function minus what we claim the limit value is. Do you see that that's the conclusion of the definition? The conclusion of the definition is whenever we get within delta of A, the conclusion is that our y values get within epsilon of L. You guys have all heard the phrase, we've assumed the conclusion. That's what we've just done. We've just assumed the conclusion. And this is why people sometimes get confused with these proofs. Okay? In my scratch work, I assume the conclusion and then try to find some other key fact that will be helpful for me. Okay? So all I've done here is assume the conclusion. What is our f of x, though? In this case, I think it was 4x minus 5 minus 7. which simplifies to be the absolute value of 4x minus 12. Okay, now I've done this a few times, so I kind of know the direction we're trying to go. Oftentimes, these epsilon delta proofs require ingenuity. Okay, you got to come up with something very clever to get through them. For these linear ones, and this is the type of proof that I'm going to ask you to do, it always works this same way. So always what I'm going to try to do is I'm going to try to build the expression x minus a out of this. So I'm trying to build the expression x minus a. Well, who's a in this proof, in this problem here? Who's our a value? 3. Yeah, folks, always through these problems, make sure you can identify a, make sure you can identify L. It'll help you keep things straight. Okay? So I'm trying to build the expression what?
X minus a.
The absolute value of x minus, but who's playing the role of a? 3. So I'm trying to build the absolute value of x minus 3. Do you see that we could get there? You see we're not too far off from that? Okay, I'm going to do this in a couple steps. Okay? This is the absolute value of 4 times x minus 3, which is equal to the absolute value of 4 times the absolute value of x minus 3. Which is equal to 4 times the absolute value of x minus 3. Folks, I'm not, save yourself some room. I'm not going to be able to fit this on here, hopefully. So the point is that if we assume our conclusion, if we assume the conclusion, we find that epsilon is greater than 4 times the absolute value of x minus 3. Or if I solve this expression now for x minus a, that's what I'm trying to do, we get that epsilon over 4 is greater than the absolute value of x minus 3. Whenever you've done this for these linear problems that I'm giving you, this will be your formula for delta. Okay? So you start by assuming your conclusion, the last line of the definition of the limit. Okay? You start by assuming your conclusion, and you try to build the expression x minus a, isolated. Then whatever's on the other side, that will be your formula for delta. Okay? So step 3 is the actual proof. Why wasn't step 2 our proof? What did we do in step 2 to get to what we wanted?
Scratch work?
Yeah, what did we do in the scratch work that makes it not valid?
We just assumed.
We assumed what?
That 7.
Yeah, so we assumed our conclusion, right? We assumed the last line, and then so we did the proof backwards, essentially. So now we need to start over and do it in the right direction. So this is the part where you have to get this lingo correct. Okay? I'm not saying you have to write it my way, but if you deviate from it, there's a good chance you'll do it wrong. Okay? So there are other ways to say this, but I feel like until you've gotten really comfortable with these proofs, it's hard to understand the difference between the correct wording and the incorrect wording. So I would just say, just copy what I do, but verbatim. Okay? So here's how it goes. We say, let epsilon greater than 0 be given. Okay. How did the definition work? We're going to follow the definition. The definition said for every epsilon greater than 0, what can we do? If it's going to be the limit, we need to be able to find a delta. So what are we going to do here? Well, we've been told what epsilon is, so now we're going to set delta equal to epsilon over 4. Where did that epsilon over 4 come from? It came from our scratch work when we assumed the conclusion. Right there. So we set delta equal to epsilon over 4. So that whenever 0 is less than the absolute value of x minus 3, which is less than delta, we have, so do you see what I'm doing here, folks? I'm basically running through the definition. We were given an epsilon greater than 0, we let it be given to us. Then we went ahead and specified what the delta had to be, so that as long as our x values get close enough to a, our f of x values we want to show will get close enough to what we claim the limit is, L. Okay. So we have, and now I'm going to start back here with f of x minus 7. What's our function? Well, it's 4x minus 5 minus 7. What is my goal here? Let's go back and look at that definition. What's my goal here? My goal is to show that this expression right here is what? Less than epsilon. That is my goal. Okay. And I can only use the stuff that I've given myself in this proof, meaning we were given epsilon, and I said, hey, we can set delta equal to this. This part is going to seem a little bit familiar, but what we're actually doing is we're running through the proof in the correct direction. We're not assuming our conclusion this time. Okay? So this gives me the absolute value of 4x minus 12, which is equal to 4 times the absolute value of x minus 3. All right, this next step is the critical step. What do we know about absolute value of x minus 3? We know that it is less than delta. Okay? So sometimes folks have a hard time with this. Let me write over here. X is less than 4. Okay? So if I saw the number 2x, what do I know this is? Well, if x is less than 4, then what do we know about twice x?
It's less than 8.
We know that it must be less than what?
8.
Less than 8. Okay? So if I know this, then this is equally true. Okay? What do I know about the absolute value of x minus 3? I know that it is less than delta. So what do I know about 4 times the absolute value of x minus 3? I know that it is less than 4 delta. Okay? Absolutely critical. This is an equal sign. This is an equal sign. This is an equal sign. These are all just rearranging. What is this expression here? An inequality, a less than symbol. Why? Because this expression is less than delta. Now this next part is just finesse. What do we know delta is? What do we set delta equal to? We set it equal to epsilon over 4, right? How does this expression clean up? We end up with just an epsilon here. Okay? Let's run through this. Our goal in the limit definition was to show that as long as we get within a certain distance of A, our range values will get within a certain distance of L. Did we show that? Well, we said give us the distance you want to get within the true value of the limit, what we think it is. Okay, fine. As long as your x values get within epsilon over 4, we think we can make that happen. Sure enough, what does this represent? This represents the distance between the y values and what we think the function is. And what did we eventually show? We showed that this distance is less than epsilon. Okay? So the kind of the upshot is we show that this is less than epsilon, which is what we were trying to show. So at this point, folks, you do what math people do. You draw yourself a box and you fill it in. I don't know why. That's how we say it's the end of a proof. That was tough, folks. Doesn't get any tougher, though. That's all you have to do.